Hi there guys, so in this video I'd like us to go through the trigonometric functions sine, cos and tan. So we're going to start off with the sine function. So below you can see there's an equation, y is equal to a sine x plus p in brackets and then plus q outside the bracket. So we're going to have a look at what each variable does to this sine function, and then we're going to swap the sine for the cos and then see what happens there, and then do the same for tan. Okay, so first of all, if you look at the graph in front of you, we have the y-axis on our left-hand side and the x-axis in the middle. Okay, and the x-axis goes from 0 to 360 degrees. The markings for 360 degrees isn't there, but I do have the markings for 100, 200 and 300, so you can kind of estimate where 360 is going to be. And then also the y values goes up till 5 and down till -5. Okay, so we are quickly going to see what happens when I increase a's value. So a's value currently is at 0, that's why we have a straight line. But we'll see what happens when we increase a's value to 1, what happens to the graph. Okay, so this is the normal sine graph. You can see it has an S shape like that, starting at 0, going up to a maximum point of 90 and 1, and then down to a minimum point of 270 and -1. It also has x-intercepts at the origin, so that's where x is 0 and y is also 0, and then another x-intercept at 180 and 0, and then a last x-intercept at 360 and 0. I say last, but it's not necessarily a last x-intercept. It's just that for this domain of, or for this, for this restricted domain of 0 to 360, then we are only talking about those 3 x-intercepts. But if you continue, and a sine graph continues indefinitely, so if you go all the way to infinity, you'll find plenty more x-intercepts. Now, let's see what happens when I increase a's value. So if I make a, let's say 2, can you see how it stretches the graph? So it stretches the graph vertically. We call a the amplitude because it stretches the graph vertically. Okay, if I make it 3, it stretches it even further, 4 even further, 5 even further. You can see when a's value is 5, the maximum point is 5 and the minimum point is -5. So it just keeps stretching the graph out. If I have it at 3, you can see the maximum point at 90 is at 3 and the minimum point to 70 is at -3. Okay, so I'm just going to play this out for you and see what happens. Also notice now what happens when a becomes negative. You see that reflection there? This is now because a is negative. And there it goes back, that's when a is positive. And one more time, there's the flip. Okay, so if a is negative, the graph kind of flips like that. So instead of going up first, it goes down first. So if this was just a regular sine graph, let's make it sine of -1. -1 times sine. Then our minimum point is actually at 90. And our maximum point will then be at 270. Okay, so it just flips, right? Okay, so let's just continue. There you go. Now we're going to have a look at what happens to that p value when you add something to the x. Okay, I'm just going to leave a at 2 just so we have a more, wider graph, I guess. So I'm going to play with p's value and we're going to see what happens now. P's value will determine the left and right movement, as you'll see now. So if p increases, the graph goes to the left, and if p decreases, the graph goes to the right. Let me do this slower. So if I increase p, notice the graph is going to the left. Okay? And if I decrease, let's say I start minusing, it goes to the right. Okay, now watch what happens. Okay, so let me just get p to 0 quickly. Okay, so p is at 0. Watch what happens if I increase p by 90 degrees. Oops, that's too much. There we go. There, p has been increased to 90 degrees. Do you notice that this is now a cos graph? This is actually a cos graph, and I'm going to demonstrate that when we do cos again. So this is actually a cos graph, and that's when the graph is shifted 90 degrees to the left. Okay, if you keep shifting, you can just see it shifts between cos and sine all the time. Let's see what happens when we play with q's value. If I move q up, let's say I move q up to 1, then the entire graph moves up with 1 unit. If I make q 2, then the graph lifts up 2 units. So instead of starting at 0, it starts at -2 on the y-axis. And vice versa, if it's negative, it will start at whatever that negative number is. Okay, the y-intercept will be whatever that q's value is, and then it just goes from there. Okay, this is of course only if the graph is not moved left or right, because if it does move left or right, then you can see the y-intercept changes. Okay, so the cos function is similar to the sine. It also has an amplitude that stretches it out, right, or condenses it, and if it's negative, it reflects. Okay, here you see the reflection happening, and then it stretches out, and the smaller the value, it condenses smaller, or it squeezes together like that. Okay, and there's the reflection again when it's negative. Okay, let's just leave a at 1 and see what happened when we increase the p value. There the graph moves left and right and so forth. Okay, so I'll just leave p's value at 0. But notice a cos graph has a minimum point at 180, and it has a maximum point at 0 or at 360 degrees. This is for the regular cos graph. If I increase the amplitude, then that maximum and minimum value changes. Okay, if I have it at 5, oops, okay, let's make it smaller. Let's make it at 3, for instance. Okay, if I have it at 3, then the minimum point is still at 180, but it's -3 now, and the maximum points will be again at 0 and 360, but the maximum points is 5 in this case. I mean 3 in this case. So just like sine, p's value will also shift the graph left and right, and if you shift it by 90 degrees or left or right, you'll end up with sine graphs. Let's just move it 90 degrees to the right. That's if we say -90, and there you go, that's a sine graph. And if we move it to the left with 90 degrees, and that is a negative sine graph. Okay, so that's the co-functions we learned when you add 90 or when you subtract 90. Okay, p again just moves the graph either 1 unit up, 2 units up depending on q's value, or 1 unit down, or 2 units down, or even 3 units down. Okay, now remember the up and down shift can also happen while there's an amplitude change. They don't need to happen independently. Okay, both or all 3 variables can work at the same time. So here we have our loss function tan, and tan has asymptotes at 90 and at 270. That's why you see the graph, it kind of goes like this, and then there's this discontinuation, and then there's another tan graph, and then there's again a discontinuation, and then it continues like that. Okay, and it just has a short period of 180 degrees. So it goes from 90 to 270, that's one period, and then from 270 to another 180 units after that, 80 degrees, sorry. And so let's look at what happens when you increase a's value. So if I increase a's value, can you see how the graph thins out? It kind of also gets stretched vertically. So that stretch looks like it's thinning out. And then when we make a small a value, let's make it 0.5, 0.4. Can you see what's happening? And watch when it goes to the negative. Boop, there's a flip. Okay, so there's that reflection that happens again. Okay, so if you watch it play slowly, See, there's the flip. Okay, there's it stretched out, thinning, condensing, and then gets stretched out again on the flip side. Okay, we're just gonna leave A at 1, and then we're gonna see what happens with P and Q. So P does the same thing. It shifts the graph left and right. Left is when it's positive, right when it's negative. And let's see what Q does. It shifts the graph up and down depending on Q's value. So if Q is positive, it goes up. If Q is negative, it goes down. And that's it. Okay, lastly, we're going to look at what a multiplication to that x variable does. And so I've put the letter b next to x. We're back at the sine graph now. And we're going to see what this variable b does to the graph. So b is something being multiplied with the x. Okay, so let's consider b to be 2. Okay, so let's say it's sine 2x. Can you see now that the graph was kind of squished together, and you can fit two sine graphs within the same period of 360? Notice when I make b 3, can you see that we can fit 3 sine graphs now? Look at how many camel humps there are. 1, 2, 3. That's in the space of 360 degrees. And this is because b's value is 3. So whenever you multiply that x by something, it means you can fit more sine graphs in the usual period of 360. And let's see what happens when we decrease b's value. So if you make it, let's say a half, instead of 1, it's now a half. Can you see it stretches the graph out? It stretches it out horizontally. So that's 1, and this is a fraction. It's stretching it like super. Okay, there's even a straight line. Okay, so there you go. Let's just watch this in slow motion. Cool. Nice. Squish together and expanding in the other direction. Cool.